Nano-drones have stringent computing constraints and low-resolution cameras. Despite their constraints, we aim to enable complex vision-based tasks aboard nano-drones, such as 3D dense reconstruction, a key task in robotics. Top-performing 3D reconstruction methods leverage neural radiance fields, which exceed nano-drones' memory and computational capabilities by orders of magnitude. We propose Tiny-DroNeRF, a lightweight NeRF algorithm tailored for MCUs, obtained by performing parameter optimization on the state-of-the-art Instant-NGP. Tiny-DroNeRF reduces memory requirements by 95% compared to Instant-NGP through hyperparameter optimization, with only a 0.2 decibel decrease in reconstruction quality, measured with PSNR. Nano-drones have limited memory capacity to store the training images, which makes it unfeasible to store the entire train set on a single drone. We introduce federated learning. Multiple drones, called a swarm, each seeing different parts of a scene, train locally and periodically share only their weights. The unfeasible centralized approach is the upper bound in which we assume a drone has access to the whole dataset during training. In the federated approach, each drone sees only a subset of the dataset, corresponding to a part of the scene. One drone, called the coordinator, performs a short pre-training phase and subsequently shares the resulting initial model with the rest of the swarm. Next, federated learning starts. All drones perform local training, and then they transmit their updated model parameters to the coordinator. The coordinator aggregates the models using the federated averaging algorithm, which computes a weighted average of the received parameters, and then sends the resulting model back to the swarm. The single drone approach shows poor reconstruction performance. Each drone can only reconstruct what it sees at training time, and struggles with completely unseen views. The federated approach can reconstruct 360-degree objects without sharing images, only weights. PSNR improves by 1.7 decibels compared to the best-performing single drone model, Drone 4, in the example shown. The federated approach overcomes the limitations of the individual drones and produces a complete reconstruction of the object. PSNR is within 3.2 decibels of the centralized upper bound, which would not fit the memory of a single drone. We acquire a new dataset with our nano-drone in an indoor environment, featuring narrow walls and 2 traffic cones. The drone flies across the space while recording from its onboard camera, its first-person view shown on the video. It is a more challenging setup than the Lego, as the images are grayscale instead of RGB and the environment is cluttered. With a PSNR of 21.2 decibels, Tiny-DroNeRF can capture the overall geometry of the corridor and the 2 cones in the environment. Tiny-DroNeRF can reconstruct real-world indoor scenes from grayscale images captured on board our nano-drone. We present Tiny-DroNeRF, a lightweight NeRF tailored for executing on MCUs. We propose a memory-efficient implementation of Tiny-DroNeRF targeting the ultra-low-power multi-core GreenWaves Technologies GAP9 MCU, available aboard our nano-drones. We lower memory requirements by 95% compared to Instant-NGP, with only a 0.2 decibel loss in reconstruction quality. We develop a federated learning scheme that allows swarms of drones to fully reconstruct objects from partial views. The federated PSNR improves by 1.7 decibels upon single drone training and reaches within 3.2 decibels of the centralized upper bound. We evaluate Tiny-DroNeRF in a real deployment scenario by acquiring a new dataset with our nano-drone in an indoor environment. With a PSNR of 21.2 decibels, Tiny-DroNeRF can reconstruct a real indoor scene from grayscale images captured on board.